Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. Today, we are going to discuss about magnetic materials and different terms related to magnetic materials. Now, when we talk about magnetic materials, so what we are going to observe here is, if we take one particular magnetic material, then if it has this property of magnetism, then the main contribution to magnetism, it comes because of electrons that are present inside the atom. So what we are going, and in this case, just like we have seen in dielectric materials we have seen that when we talk about polarization, they're completely dielectric materials. We talk about polarization, and the polarization, it exists because of formation of electric dipoles. Similarly, when we talk about magnetic materials and about their magnetism, here we have to talk about here magnetic dipoles also. And what we are going to observe here is that this magnetic dipole, it is not just mere separation of charges, okay, separated by a small distance, but this is because of existence of electron going for spin motion as well as orbital motion. We know that when we consider an atom, in atom we have positively charged nucleus, and this positively charged nucleus, it is we have electrons which are revolving in various orbits around the nucleus. And what we are going to observe here is, if we take such electrons, when they are moving around the nucleus, not only they'll revolve around the nucleus, but when they are moving, they'll rotate about own axis. So they are going to rotate about their own axis. And here, contribution to this magnetism, it comes because of orbital motion of electron as well as because of spin motion of electron. So here the concept of understanding magnetism in a material, it is completely different to polarization, which we have discussed in dielectric material. So here, as I said, that magnetism in a material, it arises because of magnetic dipoles. And here, magnetic dipole, it is not just merely two poles, just like if we take a bar magnet. Suppose if we talk about a bar magnet, and in bar magnets we have north pole and south pole. And if we take this bar magnet, this north and south pole, they are separated by a small distance. And of course, this arrangement where we have two different poles separated by a small distance, this arrangement, it is called magnetic dipole. But this magnetic dipole will apply when we talk about a bar magnet. But what we are going to observe here is, when we are considering magnetism arising in each atom of magnetic material, then what we are going to understand here is, this role of electrons is very, very important. So here we have to consider these dipoles arising because of electrons moving in orbits, also because of their spin motion. And why we have to talk about this magnetism arising because of orbital motion and spin motion of electron? Because we have studied about current loop. So when we talk about current loop, where we have flow of electrons around a loop. So when we consider flow of electrons around a loop, we know that when current flows across a closed circular loop, then there is a magnetic field developing in a direction perpendicular to current direction. So there will be field, magnetic field arising. So by taking that same concept, here we have electrons moving in various orbits, and this motion of electron in various orbits is nothing but circulating current. And this current, and we know that we assume orbitals to be circular, so we consider them, of course we'll say elliptical, but here we can consider them to be a circular orbits which has got radius r. And when we have these electrons moving in circular orbits, this is just like flow of electrons, flow of current. And because of this current flowing, what we are going to observe here is, because of spinning as well as orbital motion, there will be magnetic field produced, and this direction of magnetic field, it will be perpendicular to the direction of flow of electron, or perpendicular to the surface area of the atom. So here, main role to magnetism, it comes because of orbital and spin motion of electrons, and that too. And of course, there is one more contribution. Contribution is when we talk about this nucleus. So when we consider nucleus, and in nucleus we have, of course, two types of particles: neutrons, which do not have any charge, but we have protons, which are positively charged. And what we are going to understand here is, inside the nucleus, these protons also spin. So there will be spinning of protons, and because of spinning of protons also there is some magnetism arising, or we can also talk in terms of magnetic movement, but its contribution is very, very negligible. So by taking into consideration all these contributions, we are going to see how magnetism arises and what are the different types of magnetic materials existing. So first, before discussing about these magnetism arising in the material, first we'll try to get familiar with some of the basic definitions related to magnetic materials. So when we consider such basic definitions, first we are going to talk about magnetic dipole. So here, now first, in order to understand about magnetic dipole, I have taken simple example of a bar magnet. So if we take this bar magnet, and we know that in a bar magnet we have two opposite poles, north pole and south pole, and this north and south pole, they are separated by a small distance 2L. Okay, so if we have a system where two equal and opposite magnetic dipoles are separated by a small distance, then such arrangement it is called as magnetic dipole. So here magnetic dipole, as you can see here, is each tiny dimension of magnetic material. So when we talk about tiny dimension, here we are talking about atom. So when we consider an atom in a magnetic material, so it will act as a magnetic dipole, and this magnetic dipole, it is going to produce magnetic moment depending upon the alignment of its magnetic moment vector with respect to the applied external field, magnetic field, and this applied external field, it is called as magnetizing field or magnetic field intensity. Okay, so first we have taken one simple example of bar magnet. And in case of bar magnet, how we are defining a magnetic dipole? It is a system which consists of two equal and opposite magnetic poles. Actually, these are magnetic poles which are separated by a small distance. And each atom, of course, we can also define a dipole by considering an atom inside a magnetic material. Each atom will also act as magnetic dipole. Okay, and when each atom it is behaving as magnetic dipole, then it will have magnetic moment associated with it. But what we are going to see here is when we get all those atoms together, then magnetic moment vectors of all these atoms, they will be oriented in different directions. So depending upon the alignment, whether we have parallel alignment, anti-parallel alignment, or there is no spin alignment, based on that magnetic behavior, or we can say that magnetism of different magnetic materials is going to change. Now here we are, because we are talking about a bar magnet, so when we have a such bar magnet where we have two equal and opposite poles separated by a small distance, then in such case how we can get magnetic moment? And usually magnetic moment, it is represented by symbol mu. So if we consider this magnetic moment, generally it is defined as product of its pole strength and distance between the two poles. So what exactly is pole strength? I think we have done a small experiment in our plus 2 level. What we have done, generally we'll keep one bar magnet at the center of paper, and then what we'll do, just we'll take one compass, okay, and then we'll start moving this compass in the vicinity of this bar magnet, and depending upon the direction of movement of this needle, we are going to draw magnetic lines of forces. So these magnetic lines of force, they represent the pole strength of a particular pole. So here what we are going to observe here is, so when we consider magnetic moment, it is a product of its pole strength and distance between the two poles. So that is called as magnetic moment of a dipole, magnetic dipole. So it is just like our electric dipole. In case of electric dipole, we have considered product of charge into distance between two charges. And here we have taken, of course, pole strength and distance between two poles. And what is the unit for magnetic moment? It is taken as ampere meter square. So here units will be ampere meter square. Whereas when we have considered magnetic moment of electric dipole, what is the unit we have taken? There we have taken it to be coulomb meter. Now, this is the case when we have considered simple case of a bar magnet. Whereas, as I told you, so here when we talk about magnetism, Here we are going to talk in terms of orbital motion of electron or spin motion of electron. And when we consider this orbital motion or spin motion of electron, we have to take into consideration current loop. So this current loop, it is very important factor when we talk about magnetism. And what is current loop? Where we take circular coil of wire, and through this circular coil of wire we have flow of electrons. So when we make current flow along a circular coil of wire, then what we'll observe here is, here magnetic field, it will be produced in a direction uh, perpendicular to the direction of flow of current. So when we have such current loop, and because of that current loop, suppose if current is flowing in this direction and perpendicular to flow of current, we have magnetic field arising. Then in such a case, when your current loop is acting as a magnetic dipole, then what is the magnetic moment of such current loop dipole? In that case, what we are going to observe here is, it's magnetic dipole. Here we, as you can make out in our case, in case of current loop, magnetic dipole is arising when current flows in a conducting wire. Actually, we are taking here circular conducting wire. So we have taken circular conducting wire. So here we have taken circular conducting wire, and when current is flowing in the circular conducting wire, so magnetic dipole is arising. So in such case, how to define its magnetic moment? In case of bar magnet, we have taken its magnetic moment as pole strength into distance of separation between the poles. But here in this case, as we cannot make out north pole and south pole, then how to define magnetic moment in this case? So in this case, magnetic moment, it is defined as the product of current passing through the wire and cross section of the wire. So if you take this magnetic moment due to current loop as mu m, then it is current into area of circulating orbit. So what is the current? Current is I. And of course, because we have considered circular conducting wire, so its area will be pi r square. So this is the definition for magnetic moment associated with current loop. And what is the unit? So when we consider units, so units for this magnetic moment will be ampere meter square. So this ampere, it comes from this unit for current, and of course this meter square, it comes from area of circulating orbit. So this is the unit for magnetic moment of a current loop. So in this figure you can see, this is about the orbital motion of electron. So we have a revolving electron in an atom, and it is giving rise to magnetic moment. So as you can see here, I have taken orbit, okay, and whose radius is r. So we have flow of electrons in this direction. Then what we are going to observe here is, of course, here we have our of course angular momentum as well as magnetic field, which is being produced, okay, in a direction perpendicular to flow of current. So when magnetic dipole, okay, here in this case, magnetic dipole, it is not simply two equal and opposite poles, but it is an atom consisting of charged particles like protons and neutrons. If it undergo orbital motion or spin motion, so it will produce magnetic moment. Since motion of charged particles, it is considered as closed electric current loops, which in turn produces magnetic moment. And not only, of course, orbital motion, as I said, we know that when electron is moving around the nucleus, it spins about its own axis, and that spin, it is taken as magnitude plus half or minus half. So why we are taking this magnitude of spin motion as plus half and minus half? Because when it is rotating about its own axis, it will not go full rotation along a circle, but what it will do, it will move half clockwise and then it will move half anti-clockwise. So that's why magnitude of spin motion, it is taken as plus half or minus half. And as I am telling you, magnetism behavior completely we are going to discuss based on this current loop concept. So now coming to next definition. Next definition is magnetizing field or magnetic field intensity. So we know that when we are talking about current loop, sometimes if we keep a material which is magnetic in nature in external magnetic field, then here we talk about magnetic lines of force from external magnetic field entering that particular material. Here we talk about penetration of magnetic lines of force from external applied magnetic field into the material which is placed in that field. So just like we talk about permittivity of dielectric material, here we talk about penetration of magnetic lines of force, and there is one unique name given to penetration of magnetic lines of force. It is called as permeability. So permittivity, it comes when we talk about dielectric materials. So permittivity, it comes when we talk about dielectric material, and then permeability, it comes when we talk about, so permeability comes when we talk about magnetic material. So permittivity, it is related to dielectrics, and then permeability, it is related to magnetics. Okay, but more or less meaning is same. Suppose if you are considering permittivity, permittivity is here also allowing, or it explains about easily polarizable nature, or also we can talk about how easily a material will allow electric lines of force to pass through it when we place it in external electric field. And here this permittivity, it is represented by notation epsilon. Whereas when we talk about permeability, suppose I have taken a material, okay, and I have placed it in external magnetic field, and when we talk about this magnetic field, it will have its own magnetic lines of force, and depending upon what type of magnetic material we are taking, so penetration of magnetic lines of force from external magnetic field, they will be different. Suppose if I talk about diamagnetic material, this diamagnetic material, they are unique in nature, where they won't allow any magnetic lines of force from external field to pass through them. Okay, so actually they repel a magnet. Whereas if we take paramagnetic material, there we have small penetration of magnetic lines of force. Whereas when we go for strong magnetic materials like ferromagnet, here we have large penetration of magnetic material. So depending upon what type of magnetic material we are selecting, this penetration of magnetic lines of forces will going to change. So that's why what we are saying here is, so the field in which our material to be magnetized is placed, that particular field, what is the name given to it? Instead of calling it as externally applied magnetic field, we are calling it as magnetizing field or magnetic field intensity, which is given by H. And there is one more definition. It is also defined as magnetic force experienced by a unit north pole which is placed at a given point in magnetic field. And as units are very important when we talk about these definitions, and when we take this particular magnetizing field, its units are ampere per meter. So unit for magnetizing field or external field or magnetic field intensity, which is denoted by H, it is given by ampere per meter. Now, as I told you that when we keep a material which is magnetic in nature in external magnetic field, then what you are going to observe here is number of magnetic lines of force that are passing per unit area. Okay, so that will define our next term, which is given as magnetic induction, or it is also called as magnetic flux density. Now, here before taking this term, we have to take into consideration induction property of magnetic material. What is induction property of magnetic material? As you can see here, when you keep a material magnetic in nature, in external magnetic field H, which we are calling it as magnetizing field, then what we are going to see here is some of the magnetic lines of force of this magnetizing field, they will start penetrating through this magnetic material. Okay, so it means that one contribution is coming when we talk about magnetic lines of forces. So magnetic lines of forces from this external magnetic field, they'll start penetrating this material. Apart from this material itself, it will create its own magnetic lines of force by induction. So here induction property will be there. What this material will do, it will create its own magnetic lines of force because of effect of external magnetic field. So this effect, it is called as induction effect. So there are two contributions to magnetic lines of force which are present inside the material. One is magnetic lines of force from external field, and another one is material itself creating its own magnetic lines of forces. Then in that case, how will define magnetic induction? So magnetic induction, it is defined as total number of magnetic lines of forces per unit area. And of course, as I told you, this magnetic lines of forces, they will come from two contributions. One is magnetizing field, that is nothing but our external field applied. And then due to the field induced in the material by induction. So due to the field induced in the material. So here magnetic lines of forces will be created by the material by induction or because of the effect of magnetizing field. And this total number of magnetic lines of forces per unit area, it is called as magnetic induction. Now coming to formula for magnetic induction, this magnetic induction, it is given as magnetic flux by area. So it is given as magnetic flux by area, and we know that this magnetic flux, it is given by phi, and of course area is A. So what is the unit for magnetic flux? We know that magnetic flux, it is given by Weber. Okay, so that's why, what is the unit for this B? So units for B, it comes out to be Weber per meter square, or this Weber per meter square, it is called as Tesla. Then coming to third term related to magnetic material, permeability. As I told you, just like we talk about permittivity in case of dielectric material, here we talk about permeability related to magnetic material. So here, because in dielectric material we talk about polarization, so how easily a material is getting polarized will define permittivity, and this permittivity value will be different for different dielectric materials. Similarly, when we talk about magnetic materials, here we are talking about permeability, so permeating. So this permeability, it comes from the term permeating. So here it is permeating. As I told you, when I take a magnetic material and if I keep it in an external magnetizing field, then what we are going to observe here is this magnetic material, it will allow some of the magnetic lines of forces of magnetizing field to pass through it. And to how much extent this magnetic material is allowing this magnetic lines of force to pass through it, it is given by this particular term called as permeability. Permeability is permeating, allowing magnetic lines of force to pass through it. And this permeability value will be different for different materials. Suppose again, if I take those three examples of magnetic materials like dia, para and ferro. So if we take diamagnetic materials, in diamagnetic materials, as I told you, it won't allow any magnetic lines of forces to pass through it. And suppose if I try to draw a figure, suppose if I have taken diamagnetic material, then what it will do, it will not allow any magnetic lines of forces to pass through it. Right, and when we take weak magnets like paramagnets, so what these paramagnets will do, they will allow very few number of magnetic lines of forces to pass through them. Whereas if I take strong magnets like ferromagnet, then what this ferromagnet will do, it will make large number of magnetic lines of force. You will have very high penetration of magnetic lines of force through it. So obviously permeability of dia and para will be very, very less, whereas permeability values of this ferromagnetic material will be very large. So what do you mean by permeability? Permeability, it is the ability of the medium or ability of a material to penetrate or permeate the magnetic lines of forces through it when they are placed in magnetizing field. So ability of the medium to penetrate or permeate the magnetic lines of forces, to how much extent it is allowing magnetic lines of forces to pass through it when it is placed in external magnetic field, is nothing but permeability. And if we talk in terms of definition, as we know that magnetic induction is a number of lines of forces with respect to magnetizing field H. So that's why we'll take definition for permeability as B by H. What is our B? B is magnetic induction, which is completely talks about number of magnetic lines of forces per unit area to the magnetic field intensity H. So notation for permeability is mu. So how this mu is given? Mu is equal to B by H. And what is the unit for permeability? Permeability, it is given by Henry per meter. So here till now we have discussed about magnetic field intensity. Magnetic field intensity unit is ampere per meter. Then we have discussed about magnetic induction or magnetic flux density. Its units will be Weber per meter square or Tesla. Then we have permeability, whose units are given by Henry per meter. So these, just remembering all these units are very, very important. Then coming to next term, so just when we are talking about permeability, there is one more term which is given as mu r. And what is this mu r? Mu r represents relative permeability. Okay, so if we try to again compare with dielectric materials, there we have discussed about relative permittivity. And this relative permittivity, it is also called as dielectric constant, and it is given as epsilon r. So when we are talking about permeability, so here relative permeability, obviously this relative permeability which is given as mu r, it is the ratio of permeability of a medium to the permeability of free space. So when we talk about relative permittivity, we have taken as permittivity of the medium to the permittivity of free space. So here when we talk about relative permeability, it is ratio of permeability of medium to the permeability of free space, which is mu by mu naught. And what is the value of permeability of free space? It is given as 4 pi into 10 to the power of minus 7 Henry per meter. So here value of this constant value, permeability of free space, which is given as mu naught. Its value is 4 pi into 10 power of minus 7 Henry per meter. And as you can see, mu r, it's a ratio of two permeabilities which are having same units. So what is the unit for relative permeability? It has no units. Then coming to next definition, our next definition is intensity of magnetization. So what is intensity of magnetization? Again, when we try to compare with polarization process, so just like polarization vector, we have intensity of magnetization. So compared to dielectric materials, we have polarization vector. And how we have defined this polarization vector? We have defined it as induced charges per unit area, or it is defined as induced dipole moment per unit volume of the dielectric. And if we have n number of atoms or molecules per unit volume of dielectric, it is taken as n mu, where mu is induced dipole moment. Then similarly, when we talk about intensity of magnetization, and what is the notation for intensity of magnetization? M. In some, some will refer this intensity of magnetization by I also. So notation, it can be taken as I, or it can also be taken as M. And generally when we talk about magnetization process, so magnetization, it is the process where non-magnetic material is converted to magnetic material. And we know that in order to convert non-magnetic material into magnetic material, what we have to do, we have to apply external magnetic field. And when we talk about intensity of magnetization, so just like we have defined polarization as magnetic moment per unit volume, here also intensity of magnetization, it is defined as magnetic moment per unit volume. So why I'm referring to dielectric terms here? Because it will be easy for us if we try to compare definitions taken definitions associated with dielectric with definitions associated with magnetism. Okay, so there also we have defined it as magnetic moment per unit volume. Here also intensity of magnetization is defined as magnetic moment per unit volume. And here we are talking about induced charges per unit area. So here we talk about pole strength per unit area dollar. So one more definition is pole strength. So when we talk about this magnetization M, and usually this pole strength, it is given as small m per unit area. So this is definition for intensity of magnetization, which is also given as magnetic moment per unit volume of the magnetic material. And coming to units, units are ampere per meter. So as you can make out that M and our H. H is our magnetizing field or magnetic field intensity, and M is intensity of magnetization. Both are having same units. Then coming to our next term, magnetic susceptibility. Okay, so here, of course, what is the notation for magnetic susceptibility? It is given by this symbol chi. So this symbol, it is called as chi, right? And of course, we should not get it confused with our notation for wave function. Wave functions associated with the wave, they are given by symbol psi. So this symbol, it is psi, which represents wave function, whereas this chi, it represents susceptibility. So it can be magnetic susceptibility or it can be electric susceptibility. In case of dielectric materials, electric susceptibility, we have defined it as ratio of polarization vector to the electric field applied. So when we talk about magnetic susceptibility chi, so for that what we are saying here is to the extent to which a material gets magnetized, it depends upon strength of externally applied magnetic field. So what we are doing, suppose if our applied magnetic field is very weak, then we have very small number of magnetic lines of force penetrating. So their induced magnetic moment will be lesser. So as we keep on increasing our strength of magnetic field, then what we'll observe here is this magnetic moment will also increase, and parallelly, simultaneously, even our intensity of magnetization also increases. So that's why what we'll do, we'll consider intensity to be proportional to magnetizing field H. And if I take out this proportionality sign, I'm introducing one constant chi. So I is equal to chi H. And what is this proportionality constant called as? This proportionality constant, it is called as magnetic susceptibility. And if we consider definition for magnetic susceptibility, it's a ratio. And what we have in this ratio, we have intensity of magnetization to the magnetizing field. So when we come for definition, it is defined as the ratio of intensity of magnetization to the magnetizing field. And as I told you, units of intensity of magnetization as well as this magnetizing field or magnetic field intensity is same, which is ampere per meter. So that's why this magnetic intensity will not have any units. So just if we try to recollect definitions of these different units of these different terms, first we have discussed about magnetic moment. So magnetic moment units will be ampere meter square. So if we consider magnetic moment, so here in this case, if we consider this magnetic moment it has units. So when we talk about its units, it is ampere meter square. And then after that, we have taken magnetizing field. Of course, this magnetic moment, it is given by mu. And then H. What is H? H is our magnetizing field or magnetic field intensity, and units are ampere per meter. And then after that, we have taken magnetic induction, and this magnetic induction, which we are calling it as magnetic lines of forces per unit area, phi by A. So it is taken as Weber per meter square or Tesla, right? And then next, where we have discussed about permeability, so mu. So this permeability, it is given in terms of units. What is the unit? Unit is Henry per meter for permeability. And here we have come across one constant value, which is permeability of free space. What is the value of permeability of free space? It is 4 pi into 10 power of minus 7 Henry per meter. And then next we have discussed about this intensity of magnetization. So if we take intensity of magnetization, its units are same as magnetizing field, which are taken as ampere per meter. And then we have our susceptibility chi, and this chi, it has no units. So these are the different definitions related to magnetic material. Then in the end, we are going to discuss about relation between B, H and M. So there are two relations or two expressions which are very useful, which are very important also. And those relations, so when we talk about first relation is relation between B, H and M. So what is our B? B, it is called as magnetic induction. So it is called as magnetic induction or magnetic flux density. Right. And then when we talk about H, H is nothing but our magnetizing field. So it is called as magnetizing field, or what is the other name given to this H? It is also called as magnetic field intensity. So it is also called as magnetic field intensity. Right. So this is our H. And then we are talking about magnetization, intensity of magnetization. And so this M stands for intensity of magnetization. Right. So we are trying to get relation between this B, H and M. Now to start with, first what we are doing, we are considering definition for permeability. Already we have defined permeability to the extent like when we keep one magnetic material in external magnetic field, to how much extent it is allowing magnetic lines of forces to pass through it Based on that, we have our permeability mu. So what is our mu? Mu represents permeability of a medium or permeability of a material. And this permeability mu, it is taken as ratio of magnetic induction to the magnetizing field H. So from this, what is my B? So B, it is taken as product of permeability into magnetizing field H. But how can I write this permeability? We have defined relative permeability, and this relative permeability, it is taken as ratio of permeability of medium to the permeability of free space, and from this permeability of the medium, it is taken as permeability of free space into relative permeability. So mu is equal to mu naught into mu r. So in place of mu, if I substitute this value as mu naught into mu r, then after that, what we are doing, adding and subtracting mu naught h. So what we are doing, we are adding and subtracting mu naught h on both sides. Then what we are going to observe here, on right side of this particular equation. Then what I have done, when we try to compare these two steps, so in place of this mu naught mu or h, which is right side of equation 2, so we are adding and subtracting mu naught into h, where mu naught is permeability of free space. And what is the value of permeability of free space? It is 4 pi into 10 to the power of minus 7 Henry per meter. So if we do it, then after that I am considering these two terms, and in these two terms, I am considering this term as well as this term. And in these two terms, if I take out mu naught h outside, then from this term we are left with mu r, and from this term we are left with 1. So here we have mu naught h into mu r minus 1. But what you observe here is this h into mu r minus 1 is nothing but our m, intensity of magnetization. So in place of this h into mu r minus 1, if I replace it with intensity of magnetization m, then if I go to this step, so here what we are doing, in place of this, I am substituting m by going by this relation. So this will become mu naught into intensity of magnetization m plus mu naught into magnetic field intensity h. And if I take out mu naught common, so what I have in the brackets, h plus m. This is very important relation. So we are going to make use of this relation in numerical problems also, where we'll be given value of intensity of magnetization, or we are also given value of susceptibility, and also we are given value of magnetizing field, and we are supposed to find magnetic induction. So in those numerical problems, this particular formula is widely used. Now this is very important relation between magnetic induction B, then magnetic field intensity H, and then of course intensity of magnetization M. Now by using this relation, now we are going to get very important relation between relative permeability and electric susceptibility. So here this is now next here, of course, after getting relation between B, H and M, we are trying to get relation between, so here we are trying to get relation between relative permeability and of course magnetic susceptibility. So relative permeability, which is given by mu r, and magnetic susceptibility. So we have our magnetic susceptibility, which is given by chi. So this process, it is for getting relation, very important relation between relative permeability and magnetic susceptibility. So for that, what I have done, I am making use of this expression just now, relation which we got between magnetic induction, magnetizing field and magnetic field intensity. So when we consider this case, so here what we are going to observe here is, first again I'll take this particular formula for relative permeability. We know that relative permeability, it is defined as, so this mu, it is defined as ratio of magnetic induction to the magnetizing field, right? And apart from this, we know that relative permeability, it is the ratio of permeability of the medium to the permeability of free space. Now from this relation, we have permeability of the medium as product of relative permeability into permeability of free space. Now if I try to compare these two relations, so from this, what is our B by H? So B by H is mu R into mu naught. So we have this relation B by H. Now, what we are going to do, we are going to keep this product mu naught into mu R as it is. And what I'm going to do, I'm going to substitute this relation between B, H, M in this ratio, which is B by H. So in place of B, we are going to substitute as mu naught into H plus M. So here we have B by H, but B we can write it as mu naught into H plus M, where M is intensity of magnetization and H is magnetizing field. Now if we try to simplify it, so mu naught into mu R, it comes out to be, so this H, if I take it inside, then H by H it will become 1 plus M by H. So we'll get M by H, and this mu naught into this, if I take M by H, so ratio of intensity of magnetization to the magnetizing field, it is given by susceptibility chi, which has no units, because what is the unit for intensity of magnetization? Intensity of magnetization is given by ampere per meter. Even magnetizing field also given by ampere per meter. So that's why we are introducing one constant term chi, magnetic susceptibility, and this chi value it is given by M by H. Now on both sides we have mu naught, which is permeability of free space, so simply we can cancel it. Then we are left with relative permeability, which is given as 1 plus magnetic susceptibility chi. So this is our very important relation. So here, like as told you that this relation is used in numerical problems, okay, and here this relation is also used in order to find relative permeability once susceptibility is given, or vice versa, where we can find susceptibility once relative permeability is given. And this relative permeability and susceptibility, they are going to play a very important role when we take different types of magnetic materials. Suppose again, if I talk about this dia, para and ferromagnetic materials, what we are going to observe here is relative permeability value. For diamagnetic materials, it is less than 1. So if I take relative permeability values for dia, para and ferromagnetic materials, so suppose if I talk in terms of dia and of course para and then ferromagnetic materials. So what we are going to observe here is in diamagnetic materials, so relative permeability is less than 1. It is less than 1, but still it is positive. So it will be in just points. And when we talk about paramagnetic materials, its relative permeability value is slightly greater than 1. So it is just 1 point something. Whereas when we talk about ferromagnetic materials, we know that they have very high penetration of magnetic lines of forces. So their relative permeability, it is very much greater than 1, and it is of the order of hundreds and thousands. And similarly, when we talk about magnetic susceptibility chi, so what we are going to observe here is in diamagnetic material, this magnetic susceptibility is negative, and of course it is very small. Why it is negative? Because these diamagnetic materials will not allow any magnetic lines of forces to pass through them. Okay, so actually it repels. So that's why we take its susceptibility to be negative, and also we'll find that magnetization direction is opposite to the applied field. And when we talk about paramagnetic materials, so their susceptibility, it will be positive, and as well as it is small. And why it is positive? Because direction of magnetization is same as applied field, but because very few number of magnetic lines of forces are passing through it, so that's why susceptibility value is small. But whereas coming to ferromagnetic material, here also positive, because direction of magnetization is same as direction of magnetizing field. And what you are going to observe here is because they have high penetration of magnetic lines of force, they have very high magnetization values. That's why their susceptibility will be very larger. So we'll try to compare different magnetic materials in terms of parameters like relative permeability and susceptibility. So today in this video, we have come across how exactly magnetism arises in a material and how we can assess magnetism occurring different materials by taking different terms. So I hope you are able to understand about these magnetic materials, and then I'm going to stop my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.